We're going to be demonstrating the synthesis reaction. This is when two elements react together to create a compound. These are the reactants, and this is the product of a synthesis reaction.
We are going to demonstrate a decomposition reaction. So you're going to have two atoms bonded together, and that's going to be your reactants. Then they break apart. There's your two products. Decomposition.
A single displacement reaction is a type of chemical reaction where an element reacts with a compound and takes the place of another element in that compound. This type of reaction is typically pictured like this. A plus BC equals AB plus C. So the A and BC, the BC splits apart, the B goes with the A, and the C is left over in the final product.
Alright, so we are doing a double displacement reaction. We are going to do lead nitrate plus lithium chloride, and this is represented here. These are the reactants. The blue represents the lead, the clear Legos represent the nitrate, the orange represent the lithium, and the black represent the chlorines. So whenever this reacts, we're going to have the blue or the lead switch and go with the chlorines to form lead chloride, and the two clears and the two oranges will come together to form 2 moles of lithium nitrate. So these are our products, and the orange, clear, and black Legos are all single Legos because lithium, chlorine, and the nitrate ion all have a +1 or -1 charge, and the blue Lego has 2 spots because lead has a +2 charge in this reaction.
There are several ways to balance chemical equations, and for students that are really strong in mathematics, they might be able to balance an equation simply by inspection, just looking at it. They may use systems of equations in algebra. Some really bright students may even go as far as using matrices to balance equations. But for students that are struggling a little bit, or if you're having trouble understanding the concept of balancing a chemical equation, I'm going to go over a method here that at least will give you a little bit of a picture as to what it is when you're actually balancing a chemical equation. Law of conservation of atoms says atoms in a chemical reaction aren't created nor are they destroyed. Well, if I look at this, I've got 1 magnesium and 2 oxygen on the reactant side, but on the product side I've got 1 less oxygen. And what sometimes people may be tempted to do is change a subscript here, but we can't change the formula for the compound. So to balance this equation, we're going to put numbers out in front of here, coefficients, multipliers, ratios. We're going to put numbers there that will make this be equal from one side with our reactants to the other side with regard to the products. So the method I'm going to use here, we're going to balance this by shapes. So I'm just going to pick a shape to be magnesium. I'm going to use a square here for magnesium. For oxygen, pretty simple, we'll probably use a circle, but I'm going to do 2 of those, and I'm going to draw them connected because that represents an oxygen bonded to an oxygen. Now on the product side, I'm going to end up with a square for magnesium and some sort of attached circle there for the oxygen. So when I'm looking at this from side to side, trying to determine what doesn't add up, immediately I notice that I don't have enough circles on the product side. So the only way I can get another circle there is to draw a whole copy of that exact same shape. All I can do is draw the square attached to the circle. So in fixing one problem, I've actually now created another. So I'll come back to the reactant side, and I need to get an additional square here. So we'll check this. We got 1, 2, 1, 2, and then here 1, 2, and 1, 2. So this tells me that for the magnesiums, the squares, I need 2 of those for every 1 O2 molecule to make 2 magnesium oxide. Now, I'll do a few more of these with this method. Again, for stronger students, you probably won't balance them this way, but if students struggling a little bit trying to learn to balance equations, this method's pretty effective. For the next one here, I've got lead 2 sulfate, making lead 2 sulfite plus oxygen. One thing you need to recognize is polyatomic ions. Here I've got sulfate. On the product side it's sulfite, so I can't treat that as a whole. You'll see some here in a moment where I'll actually treat that as one whole thing. But for now, I've got PB. I'll use a square for that. For sulfur, I'm going to go with a triangle for the sulfur. And then I've got 4 oxygens. 1, 2, 3, 4. All right, so over here, Pb was the square, sulfur, and then now I've got 1, 2, 3 of those in that one, only 3 oxygen, plus O2, which is going to be circle, circle. So I see 1 square on each side, 1 triangle on each side, but the problem here is with the oxygens, with the circles. I don't have enough on the reactant side. So I'm going to draw another one of these. All right, so now I've definitely got more circles here, but I've messed up some other things. I have messed up the leads represented by the squares. I've messed up the sulfurs represented by the triangle. So I want to fix that before I worry too much about the oxygen. The oxygen here, diatomic, but it is alone, so that might be an easier fix later on. So I'm going to draw another one of these PbSO3s. So now as I look at this, I can see 1, 2 squares, 1, 2 squares. I've got the triangle, 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 triangle. So the squares and triangles are good. Now let's count up the circles. I've got 8 of them here, and here I've got 3, 6, 7, 8. So those balance as well. 1, 2, 3, 4, 5, 6, 7, 8. Over here, 1, 2, 3, 4, 5, 6, 7, 8. So this balances 2 of those. We'll make 2 of those when it decomposes according to this reaction, and 1 O2. So my coefficients, or my ratio here, is 2 to 2 to 1 as the equation is written. For the next one I've got a single displacement reaction here where we've got iron reacting with sulfuric acid to make iron 3 sulfate and hydrogen gas. So again, I'll start off with assigning shapes. I'll use a square for the iron. Now in this one I'm going to do this a little bit different because I recognize this polyatomic ion present on both sides. I'm just going to use one shape to represent that whole entire polyatomic ion. So I'm going to draw my hydrogens, and I'm going to let triangles be the hydrogens. There's 2 of them. And for sulfate, I'm going to use a circle. Now again, that circle represents the whole SO4, and I'm doing that because it is an unchanged polyatomic ion in this reaction. So it's going to make 2 irons bonded to 3 sulfates, and then 2 hydrogens in the diatomic hydrogen gas there that is produced. All right, so as I start looking between the 2 sides, I immediately recognize that there's a problem with the squares, also a problem here with the circles. One hint is start with what's more complex first. Sometimes that's a pretty good way to approach a balancing problem. So in order to do that, I'm going to go ahead and fix the circles. I've got 3 of them over here, so the only way to do that is 1 and 2 more for a total of 3 of those over on the reactant side. Alright, so I fixed the circles. I've got 3 and 3. I have a problem with the squares and a problem here still with the triangles. So I need another square. Since it's just iron, it's by itself, I can just simply draw that square, again just representing atomic iron here. And then diatomic hydrogen on the other side, I need 2, 4, 6 triangles. I have 2. And again, the way to get 6, I have to draw that whole thing again, so it takes 3 of those diatomic hydrogens to give me the 6 that I have there. So let's check and see if things add up. 1, 2 irons, 2 squares, 1, 2. We'll go to the triangles, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So those are good, and the oxygens. 1, 2, 3. 1, 2, 3. Everything adds up, so there's 1, 2 of these. 1, 2, 3 of those makes 1 iron 3 sulfate and 3 diatomic hydrogen gases in that one. Alright, for one more, an acid-base double displacement reaction, strong acid reacting with a strong base here. This one, we've got this polyatomic ion that's present here and here, and one other thing to look for with polyatomic ions is anytime there is a hydroxide if you have water present, rewrite the water as H with OH, and we're going to treat this as a hydroxide, and we're going to count that separately when we count the hydrogens. So I'm going to start over here with my H2SO4. I'm going to let triangles be the two hydrogens, and I'm going to use a circle for the SO4. For sodium, I'm going to use a square. I'm doing the sodium hydroxide up top here. And for the hydroxide, I'll use a rectangle here for that one. All right, so this is my H2SO4, and this is my Na and my OH. All right, and since the products are down below, this one takes a little more space. I'll slide down here, and for my sodium, that would be the square. Going to be two of those with a sulfate, which was a circle. And now with the HOH, and this is where you got to be careful in the counting, I'm just going to use a triangle to represent the hydrogen, and then the OH I'm going to represent with the rectangle, treating that as this same polyatomic ion that we have. So clean this up a little bit, draw a diagonal through here. These are my reactants, these two things, and these are my products. So as I start through this, immediately I notice two triangles here. I don't have enough triangles on the product side. The only way to get that is to draw another whole rectangle triangle shape. All right, so I fixed that, created another problem. Now I got a problem with the rectangles, so I'll move up to this structure on the reactant side, and I got to draw another square with the rectangle. So as I observe this, it looks like things add up. Let's check it. I see triangle, triangle on the reactant side, and triangle, triangle on the product side. I see a circle on each side, two squares, reactant side, two squares, product side, and lastly, two triangles, or two rectangles on the reactant side, and the two rectangles on the product side. So this balances with one of these for every two sodium hydroxides will produce one sodium sulfate, one Na2SO4, and two HOHs, or two water molecules.